Today we'll be looking at the brief for descending. So in terms of housekeeping, because it's an online brief, there isn't a housekeeping. But if it was delivered in a classroom environment, I would deliver housekeeping. Saying to outline the descending configurations, techniques, and procedures used in the PA 28 for the glide descent, the approach descent, and the cruise descent. So these are the three main descents we'll be looking at for the Piper Cherokee. We'll have a look at the techniques and procedures. We'll also look at why we would do these descents as well. So motivation, build on the coordination skills learned in the previous lesson. So in the previous lesson, we learned how to climb the airplane. So now we will have a look at the same checks and procedures to learn how to descend the airplane. Learn how to handle the airplane in a safe and coordinated manner. That's to do with the airmanship side of this lesson. I'll teach you how to set up the airplane and manipulate controls so you can descend the airplane. With a high competency in the descending configurations, greatly improve the comfort and safety of your passengers. You're working your way to your recreational pilot license and then your commercial pilot license. And so when you carry passengers, you want to be able to do it as smoothly as possible. So an overview of what we'll have a look at. So objectives, that's the take-home message. We'll have a look at a revision from our climbing brief. Look at definitions that will be relevant today. Look at the forces acting in the descent. So we'll expand from the forces we looked at in Australian level. We'll look at the types of descents, which we outlined in the AIM. We'll look at the factors affecting descent, some of the environmental factors, some of the physical factors in terms of the airplane itself. We'll have a look at the applications, so the different techniques and procedures, and the configurations as well for the descents. The airmanship and threat neuromanagement, some of the threats that exist in this lesson and how we can mitigate some of those risks. I'll summarise everything, and then finally I'll ask you a few questions with the objectives. So following this brief, you'll be able to, from memory, explain the balance of the four forces in a gliding descent. As pilots, it's important we want to understand what the forces of an airplane are doing in a glide descent. State the effect of increasing weight and descent force. So this is important. We'll have a look at how weight affects our angle and rate of descent. We'll look at, in terms of dual flight versus solo flight, how it affects our airplane. State the effect of extending flaps on descent performance. And also, why you'd want to use flaps. We use flaps all the time when we're covering to land. So we'll have a look at how that affects our rate of descent and angle of descent. And then finally, explain how to enter, maintain, and exit from a descent. This is important. It forms the basis of what we'll actually be doing in flight. So, explain the balance of the four forces in a climb. So in the climb, weight is greater than lift. So how we climb? Well, we've got excess thrust, which causes our climb. Then we've got the component of weight to balance lift. So they both balance each other out. They're both equal. Then we've got the real component of weight, which also acts along the drag path over here, and thrust equals drag plus the real component of weight. So all the forces are in equilibrium. In what situations would you use a cruise climb? So you can answer these questions as well. You can pause the video. So you would use cruise climb, when you're carrying passengers and you're not in a hurry to get to your cruising altitude. It allows you to maintain the climb at 500 feet per minute. It's nice and comfortable, and you get a good forward speed as well, a good forward view. What is the configuration for the best rate of climb for the Warrior? So that's full power, nose horizon, 79 knots, and trimmed and balanced. So this is important. We use best rate all the time. And then finally, what does wind do to angle and rate? So wind doesn't affect our rate of climb. So we still climb 500 feet per minute. But if we had a headwind, that parcel of air moves along. So it makes our angle of climb a lot steeper. It increases it. Tailwind, that parcel of air moves along forward. So it makes our angle of climb decreases it. So definitions. Glide. A stabilized descent with the power set at idle RPM. So in a glide, we've got no thrust available. So how are we moving down? Well, we'll discuss this in our forces. Rate of descent, the rate in feet per minute at which an aeroplane descends, a measure of vertical speed. So when you see that word rate, it's to do with a unit of time. So here we're looking at how far the aeroplane descends, so 500 feet per minute of time. So we'll look at this in terms of the training area. When we look at the cruise descent, that's maintained at 500 feet per minute. Angle of descent, the angle between the flight path and the horizontal distance of the airplane, i.e. the gradient of the airplane. So it pretty much tells us how steep or shallow the descent is. A lot of students get confused, so the difference between angle of descent and rate of descent. Rate is to do with how far the airplane travels vertically versus the per minute of time, and then angle of descent is how far the airplane travels vertically per horizontal distance it travels as well. So forces acting in strain level, so they're all in equilibrium. So lift balances weight, so the airplane doesn't climb or descend, and thrust balances drag, so the airplane doesn't accelerate or decelerate. It stays at a constant speed. So forces acting in a glide descent. So we've got lift, which is perpendicular to our flight path. We've got a flight path over here. We've got no thrust since we're in a glide descent. We've got drag, and then we've got the component of weight, which acts towards the center of gravity. So we've got another component of weight to balance out lift, so we call that weight 1. So weight 1 equals lift. And out of these two arrows, so the weight is greater than weight 1, since it acts towards the center of gravity, so weight is greater than weight 1. So therefore, by that logic, weight is greater than lift. That one that acts towards the center of gravity is greater than lift. So which is, no problem at all. We want the aeroplane to keep on descending. So drag is greater than thrust. We've got no thrust available. We've got something called the forward component of weight. Just like we had that real component, now that weight which goes towards the center of gravity is ahead if the weight 1. So that's a forward component of weight, and that acts along the flight path. These aren't two different forces. It's just that this force also acts along our flight path. So we can manipulate the size by pitching the nose up and down. If you pitch it up, that forward component weight decreases, so you go slower. If you pitch it down, it increases, so you go faster. And drag equals the forward component of weight. And once again, all of our forces are in equilibrium. They're in a balanced state as well. So forces acting in a power descent. So it's the same thing with a few key differences. So we've got a small forward component of weight, as we've got a little bit of thrust. That thrust is able to overcome some of that drag, so we can raise our nose attitude. And by raising our nose attitude, it changes our rate of descent, so it decreases it, and our angle of descent as well becomes a lot smaller over here. So if we had some thrust, it would be able to increase our range. And once again, smaller forward component of weight, drag is still greater than thrust, but drag now equals thrust plus the forward component of weight. So total reaction 1 equals total reaction 2. So that sort of drag and lift balance out with the thrust and the weight as well. So, and if we add enough thrust, we'd be able to go back to strain level flight, and we wouldn't have any forward component of weight. So now we'll have a look at the approach descent. So the approach descent occurs at a relatively low airspeed, so about 75 knots, and used when maneuvering in the circuit pattern for landing. So when we're coming into Bankstown, we're going to use the approach configuration, and the flaps. What they allow is a steeper descent and improved forward visibility. So you'll see this in the training area. We can come at a slower but safe speed, and remember from our effective control lesson, that flaps gives us better forward visibility. And in this lesson, we've got that threat of pain in your ears, also called barotrauma. The error will be using high rate of descent, and the undesired aircraft state will be pilot incapacitation. So make sure you use a technique called I'm safe, which I'll discuss, or use moderate rates of descent, or don't fly if you're unwell. So the cruise descent. So it's a powered descent at a moderate and efficient airspeed. So you're descending about approximately 95 knots for the Cherokees. It is used to descend from the cruising altitude to circuit height. So used in commercial aviation, if you want to descend, if your cruising height is 8,000 feet, but the circuit height is 1,000 feet, you can use a cruise descent to not only start descending, but traveling forward as well at 95 knots. It would be quite inefficient to just come at your destination airport at overfly height. And it is maintained at a rate of descent of 500 feet per minute. So, it's a nice, comfortable rate of descent. You'd also use it for passengers as well. And what you'll see is you'll get a good forward speed. And also, if you've got a tailwind as well, you can get a nice ground speed as well. So glide descent, a descent that is done with the engine idling. So remember, we looked at this in our definitions. using the unlikely event of an engine failure, so providing we glide at this specific airspeed, so for our aeroplane 73 knots, we would get the best range so we can glide to a nearby airport or field. Why will the minimum drag speed achieve the best gliding range? Well, as you see, we get this total drag curve. So by maintaining that 73 knots, we haven't got as much induced drag or parasite drag. If we glide too fast, we encounter a lot of parasite drag. Glide too slow, we get a lot of that induced drag. So that's why it's that Goldilocks zone of drag, pretty much. And this is, I must stress this is in nil wind conditions, as wind can affect our range. So lift to drag ratio. So the wing's most efficient angle of attack is 4 degrees. So the engineers have worked out these numbers, plotting the values for the best lift to drag ratio. So the best lift to drag ratio is at this point, and the maximum lift is achieved with the least amount of drag. And the aeroplane will glide the furthest at this ratio. And what it means is that if you glide at that, if you glide at that 4 degrees per 1,000 feet, you'll be able to glide 12,000 feet. And this is for a cambered aerofoil as well. So for our pretty much any sort of wing on a GA aeroplane, general aviation. So the reason being because if you glide at too high of an angle of attack, you've got increased due to induced drag, and too low, you've got a lot of parasite drag. Airplanes do not have an angle of attack sensor, but we've got the next best thing, which is an airspeed indicator. So the glide speed for the Warriors is 73 knots. So the minimum drag speed occurs at 73 knots, and conveniently, our wings are attached to the fuselage at an angle of 4 degrees. So actually, this is actually for a reason, and the reason being, when you glide at 73 knots, the wings will be at 4 degrees. So in comparison to the relative airflow, you've got an angle of attack of 4 degrees. So that's conveniently not only our best lift to drag ratio, but also our minimum drag speed. So in terms of these graphs, actually it should really be the other way around, because you've got induced drag here and parasite drag here, whereas on this curve it's parasite and induced drag. But it's a little bit hard to get the scale around, so this works just as fine as well. So any variation in airspeed, then our best glide speed will decrease our range. So that's why it's really important to maintain that airspeed. If you don't, then you're not going to get that best range. That's the take-home message of this brief. It increases our rate of descent and angle of descent if you don't maintain that speed. So that's why you'll fall short and your range will decrease. So if you glide at 73 knots, this is your range, 12 to 1. So you by 1,000 feet you glide, you only lose 1,000 feet. And for if you glide at a ratio at about 6 degrees, you get a ratio of 10 to 1. So you only glide 1.6 nautical miles, and at 0 degrees, 8 to 1, so you only glide 8,000 nautical miles. So it's quite a considerable decrease as well. So that's the difference. If you're coming into Bankstown, the engine had an engine failure in the circuit, this would be the difference between making the field over there, or making the runway, or not. So factors that affect a glide descent. So we've got weight, wind, thrust, and flaps. And now we'll have a look at how it will affect our angle of descent and rate of descent. We've briefly looked at airspeed. So weight. So remember, this was in our objectives. So best lift to drag ratio is concerned with an angle of attack, and so weight does not affect our angle of descent. It's kind of like a kid versus an adult sliding down a slide. No matter who the kid or the adult is, they're still gliding at the same angle. It increases our forward component of weight, and so the aeroplane will travel faster down the same descent path. So it increases our rate of descent. Same thing, so the adult would slide down a lot quicker on the slide versus the kid. And just like with the aeroplane, so we've got a greater weight, so we've got a greater forward component of weight. So it's a quicker down the same glide path. So the range remains exactly the same, surprisingly, and it'll reduce our time in the air. So you'll really sort of see it in dual versus solo flight, where you'll still be gliding at 73 knots, range will remain the same, but you'll glide down a lot quicker as well. And so wind acts within a parcel of air. So if the glide speed is maintained, the lift to drag ratio is the same regardless of wind. So we'll still glide at 73 knots, but it affects our range. So in a tailwind, our range increases, and in a headwind, it decreases. It changes the horizontal distance, and so it only affects our angle of descent. Rate of descent stays the same as unaffected. So if you have a tailwind, that parcel of air moves along, and the angle is a little bit shallower, and so our angle of descent decreases. But if you have a headwind, it sort of moves that towards the back, and our angle of descent changes as well. So adding thrust. So we've already looked at this in a glide. In our descent allows it to overcome some of that drag, as we mentioned. As our forward component of weight decreases, our angle of descent and rate of descent decrease. So i.e. becomes shallow. So if we had enough thrust as well in the start image, we can go back to straight level flight. And if thrust was added, it would allow the aeroplane to glide further. So if we went idle descent, but we add a little bit of thrust, that's why that angle of descent and rate of descent decreases, so it increases our range. So flaps. Due to the drag from flaps, we need to lower nose to maintain the glide speed, and it results in an increased rate of descent. So easy to maintain 73 knots. What you'll see in flight as well, when you extend flaps, you'll need to lower the nose to maintain that speed. And so flaps, if you get 12 parts of lift, 1 part of drag, and if your lift increases +2, but the drag increases +1 with the flaps, the new ratio is 14:2, which is 7:1, and so our lift to drag ratio has decreased. So due to the increased forward component of weight, our angle of descent increases. So this is our forward component of weight without flaps. And then with flaps, we need a lower nose attitude to maintain that same speed, so our forward component of weight increases as well. But we use flaps all the time, and that's because it gives us better forward visibility. So coming in during landing, allows us to see the runway and traffic. And if we have a field, it's a steep approach. If we have a field and we're too high, we can make the start of the field, increase the lift so we can descend and land at a slow but safe speed, so we don't use much runway. And we've got the threat in this lesson of not verbalizing white arc. The arrow will be flap extension above VFE, and the undesired aircraft state would be an airframe damage. So make sure you verbalize white arc. So in terms of the summary of the factors, so airspeed variation, so any variation from that 73 knots would increase the angle descent, rate descent increase, weight increase, so dual or side of flight, both would, weight would stay the same since you're down that same slide, still maintaining 4 degrees, but rate of descent increases. Headwind, angle descent increases, rate of descent stays the same. Remember that parcel there. Tailwind decreases, rate of descent no change. Thrust increase, angle of descent decreases, and rate of descent is decreased as well. And if you extend flaps, angle of descent is increased, and rate of descent is increased as well due to that drag. And that forward component weight increasing. So in terms of the application, so I'll start off by doing the pre-entry checks with any of the maneuvers. So choose a good prominent reference point, because we've got that threat of poor reference point. The arrow will be choosing, you're losing your reference point, given the desired aircraft state will be disorientation. So make sure you choose a good prominent reference point, and I'll show you as well in flight. Carb heat as required, so we need carb heat below 2000 RPM. Mixture fully rich, T's, P's and green. And then you're doing a good thorough lookout, so clear right, clear centre, clear left. And make sure to clear below as well. An easier way to remember is you're going from right to left. So looking outside, carby mixture, T's and P's, and then back outside as well. So entry is done using past. So power, attitude, speed, trim. So you're going to be decreasing power, so to 2100 RPM, idle, 1500. So whenever you change power, you have to do something with feet. So you need to apply a little bit of left rudder as well, since we don't have the slipstream effect anymore, so that knows you're towards the right. So you need to apply a little bit of left. Attitude, change the attitude, whether it be half ground, half sky, 1/3 ground, 2/3 sky. Speed, make sure you're really accurate with the speed. Remember, power plus attitude equals performance. So if you set the power 1500 RPM, set the attitude half ground, half sky, you will get the desired performance, say 75 knots, and then you're trimmed and balanced as required. So in terms of the 3 descents, so we're looking at, so glide, remember we use it to get the minimum drag speed, so you get the best range to glide the furthest. So power, idle, attitude 1/3 ground, 2/3 sky, speed 73 knots, and you're trimmed and balanced. And make sure to apply that carb heat on for all power settings below 2000 RPM. So you're going to apply it for glide and for approach. Cruise descent, we use it to passenger comfort, so power 2100 RPM, attitude 1 ground to the sky, speed 95 knots. So actually in the training area we may or may not get that 95 knots, but what we want is that 500 feet per minute, and then you're trim and balanced as required. And then the approach configuration, you got 1500 RPM, attitude half ground half sky, you're applying the 2 stages of flap, and then that speed is 75 knots. And your trim and balance. So the airspeed must be in the white arc before extending flaps to prevent the airframe damage. So maintenance cycle is still ALAP from our climbing straight level brief. So attitude, want half ground, half sky. Let's say you're doing approach descent, lookout, attitude, and performance. You got 75 knots. Looking out for your target height. You're looking at you're maintaining direction. Turn slip corner, balance, and wings level. So, but you want your eyes outside, 80% to 20%, because we've got that threat of traffic. I'm in the training area. It's quite busy. We've got that threat of traffic. You'll be not having eyes outside, and your desired aircraft state will be an air proximity event. So make sure you do your ALAP cycle, and you use the clock code, and you do your pre-entry checks. So maintenance cycle CChat is once again. So let's say you don't really say this out loud. It's more of a subconscious thing. You're changing the attitude. So if you're not half ground, half sky, change it. Check, is that the new correct attitude? Hold it to see if it'll maintain. So check against your performance instruments. Are you getting 75 knots? Adjust it. Maybe you need to change your power setting. You're not at 1500 RPM, and then trim. And make sure to warm the engine to 3000 RPM. Every 1000 feet you descend for 4 seconds. So this will only be done for the glide descent. The reason being, when you're running at low power settings, the oil can't sort of really coat the engine bay properly, so the oil tends to pool at the bottom and cover the spark plugs, which can prevent, cause a loss of power. That's one of the threats. The air will be not warm with the engine. Undesired aircraft state will be low engine power, so make sure you warm the engine. So in terms of your pre-entry checks, so reference point selected, carb off, mixture for rich, T's and P's and green, and then you're doing a lookout. And if you, let's say we're doing the approach with the glide descent, so we're not using flaps just yet, but you would check white arc if you were extending flaps. Then you enter using paths, so power idle, little bit of left right, attitude, 3rd ground, 2/3 sky, speed 73 knots, and your trim and balance. Maintenance and control is done using ALAP. Remember, every 1000 feet you descend, you have to warm the engine and have a good thorough lookout. And then exit is done using A pass. So anticipate 10%, so about 3050 feet if you're leveling up at 3000 feet. Power 2500 RPM, attitude 3rd ground 2/3 sky, speed 105 knots for the Warrior, and trim. And every time you're exiting towards the normal configuration. So engine considerations: the engine must be warm due to that spark plug fouling and the high in airflow as well, which can cool the engine. Minimum altitude, so it's a new concept. It's Civil Aviation Regulation 157 here in Australia. So 500 feet AGL non-popular area, AGL popular area. So you can't go below these heights at all, only due to stress of weather. So because the elevation in the training area is about 300 feet, so it's 800 feet over non-populated and 1,300 feet over the populated. So I'll be responsible to make sure we don't go below those minimum altitudes. Balance stepping on the ball. Make sure you apply a little bit of left rudder as you decrease power, and as well, and you want that balance point in the middle. And then I'm safe, a new concept. So make sure you're well enough to fly. Are you under any medication? Any antihistamines that could affect you in your flight? Stress? Are you do you have family stress? Are you financially stressed? Alcohol? We've got the 8-hour rule where you can't drink 8 hours before flying. But if you had hard alcohol or heavy alcohol, you wouldn't drink. You wouldn't fly. Fatigue? Are you adequately rested? And have you had enough food and water? Are you adequately nourished? So in terms of threat and management, so threat of pain in your ears, barotrauma, the will be high rate of descent. The certain management technique and the undesired price state will be a pilot incapacitation. So make sure you use moderate rate of descent and use I'm safe. Low power ups, warm the engine every 1,000 feet, and loss of engine power. And the error would be, make sure you would be not warming the engine and having long periods of idle power. And the threat of terrain, poor situational awareness. Do not descend below those minimum altitudes, otherwise undesired aircraft state is a descent below minimum. So and make sure you watch out for that. So these are three main threats. Certainly, these aren't. It's not, our lesson isn't limited to these threats, but these are certainly a lot more threats that exist as well. So in terms of the summary, so we looked at the objectives, we looked at revision from our climbing brief, we looked at definitions such as glide descent, angle of descent, rate of descent. We looked at the forces acting in descent, the types of descent such as cruise, approach, and glide descent. We looked at the factors affecting descent such as wind, weight, flaps, airspeed, thrust. We looked at the application, so make sure you know those configurations as well. We looked at the airmanship and threat neuromotor considerations, so warming engine, make sure you're in balance, watching out for traffic, and then finally the objectives. So I'll give you a moment to answer these questions. So first off, explain the balance of the four forces in a glide descent. So lift is still less than weight. We've got that forward component of weight which causes the aeroplane to descend. Yeah, that's pretty much those main factors. If we add thrust, it would increase our our forward component of weight. So the effect of increasing weight on descent performance. Increasing weight, our angle of descent stays the same, but rate of descent increases. State the effect of extending flaps on descent performance. So extend flaps increases our rate of descent and angle of descent. Explain how to enter, maintain, exit descent. So enter using pre-entry checks and pass. Maintenance is done using ALAP and CCHAT. And then exit is done using a pass back into normal configuration. So thank you very much for watching.